Good afternoon, everyone. My name is Marek Mysłowski. I work for Sejsura company as a security researcher, and I would like to speak a little bit about AFL, which is not probably surprised, and how we can do it better. Okay, a few words about me. Security enthusiast, security researcher. Okay, fan of Hacker and the Matrix movie, and also I have two kids you can see here. Okay, so let's talk a little bit about what AFL is. It's an American Fuzzing Lab. Or if you don't know what American Fuzzing Lab might be, it's a wrong conference. So this is American Fuzzing Lab, and also a very good tool written by Michał Zalewski, Elkamtów, many years ago. So I just copied the definition. So it's a security-oriented fuzzer that employs a novel type of compile instrumentation and generating algorithms to automate everything, including discovery, interesting test cases, and strategy to choose another one. I did small research because I was interested when it was created. I'm thinking that it was always here, but it was not. So as an ancestor of it, it was Bunny the Fuzzer, released in 2007. Then the first release of AFL happened in 2013. And since that time, there were 230 releases. I count that, so it's literally 230 files you can download on Elkamtów webpage. So how it works in general. So everything starts from a corpus. We need to define corpus, initial test case, however you call it. Then AFL takes those and run through the application. Application creates some then it creates some feedback. And based on the feedback, the initial files are chosen for a mutation and for further fuzzing. And after every mutation that AFL does, there's kind of feedback if this was interesting, if there was a crash, or we should just skip this test case. This is general overview what AFL does and how it works. Okay, so how we can speed up the process? Well, there are 7 of different areas when we can make it better and have and achieve better results. So let's start from the beginning. So at the beginning, there is a corpus file, initial test case that you need to create it and feed not only IFL. So most of the fuzzers start either from generating itself or from a corpus. So most of the guided fuzzer, including clip fuzzer or honk fuzz, all of them relies on initial corpus, and your fuzzing will be as good as the initial corpus. So what you can do? You can, of course, start from either 0, so give nothing. AFL can do that. You can give an empty file. You need it, at least one file. It's from technical point of view, but it can be just empty, and IFL can handle that. But the time of fuzzing will be much, much longer. It was already proven by Elkamtów. You can see on his web page the test when he started from 0 file, and after some time the AFL generated appropriate, I think it was PNG file. So it works. The second thing you can do, you can just download the stuff from internet. There are a number of resources you can download from the internet. If you have PDF files, I don't know, PNG, JPEGs, whatever you want. The important thing is what is the quality of the file that you are downloading, right? You can download thousands of PDFs that will be a simple text, and you won't get much coverage of it. There are, of course, some sample sets. You can go also to Elkamtów or other GitHub pages when you can download prepared test set for video files or for graphic files. Or you can try to generate using different tools. When you want to generate, for example, video files, you can use public available decoders, create different types of the file, different conversion, whatever you want. One of the techniques is used to symbolic execution tool. I already gave a presentation about this. You can download it and see it when we use symbolic execution tool to generate valid graphic files. So we run through it, generate 100 of those files, and then feed AFL. You can go there and see the comparison, how it works with the zero file and with the stuff that we generate. Okay, so we've got our initial corpus. It's run through application, and the AFL is running. The next thing that AFL is doing is how the AFL choose the input, right? Because not every file will be chosen. It needs to decide which file is interesting. The question is, what means interesting? So AFL has a classic genetic algorithm inside. You can go through the source code and see how it works. However, there are other strategies available in the network. I choose two of them. They are quite interesting. One is called AFL rare branches. So it's a fork of AFL that promotes the branches that are executed the rare. The other one is called AFL. It's use path-sensitive fuzzing. It's quite interesting idea of how they are choosing what to fuzz next, what input should be used next. The problem is it's just the paper. So the fork is not available yet. I talked to the author of this tool, and he said they won't make it open source yet. So they're trying to add some interesting stuff because they have a very good result with it. So not yet, but you can read how they are change that. Well, the other thing is. You can do additional input during the AFL is running. Here you have two interesting options. One is master-slave mode. AFL allows you to run parallel when one of the instances are running in master, other are running in slave, and then they are feed each other, which makes more reliable. The other thing is something called concolic execution. This is a new approach that you connect or use AFL in parallel with symbolic execution engines. So how it works? So we have instances of AFL that are running, and then we have a classic symbolic execution tools. Maybe if you don't know what symbolic execution tools are, these are the tools that going through the application and try to solve and find all the possible paths by constraint solving. They are very time-consuming, resource-consuming, and they have few problems. That's why they are not used itself to validate the application. But with the AFL, they have very good results. And right now, there are 3 public available. You can download it, test it. I've seen all of them. One is Munch. The second one is Driller. And last thing, which is quite new, is QSIM. And maybe a few words. So Munch is a platform that takes a CLI, which is a very popular symbolic execution tool, and just run it first. Whatever CLI throw up, it goes through the AFL, then AFL fast from some time, and then it's going back to the CLI, and CLI generate new test cases again. Very simple, very painful to install. The second one is Driller. Driller is much more advanced. It uses not only AFL, but also Ang platform. And it works like this, that AFL is working, and when the AFL is saturated and it cannot find anything more, then the Ang platform is running with the AFL map. So then they try to find at least one path that haven't been found by AFL. When they find it, they feed it back to AFL, and AFL starts running further. You can also go to web page and download it and test it. The third one, very interesting tool that I've seen recently, it's called QSIM. It's not exactly concolic execution because it doesn't use symbolic execution for a test case generation. It uses pin tool and try to solve the constraint like loosely, so it's guessing the constraint, doesn't solve them, but this causes that it works much faster than concolic execution. The other advantage is that you need to recompile your application again for a concolic execution, because for every symbolic tool, you need to compile it to immediately language instead of a binary. There is a PDF also, it's available on a GitHub, but if you go to the PDF, there is a link where you can download QSIM. Okay, next part that is very important with AFL is crash detection. So AFL is looking for crashes. If your application doesn't crash, AFL won't report that. It's very simple. But sometimes it's not so easy. So when you have, for example, buffer overflows that don't cause a crash, AFL won't report it. So we need to make it more crashable than normally. We have few methods, of course. I just mentioned the most popular ones. One is address sanitizer. Is a tool used by Clang compiler. It's at all the checks for a memory read-write. And if something's wrong, it just crashes. So the trick is, of course, there is always a trick. It works nice, but there is a huge overhead in memory and in speed of your application. And for 64 applications, it's not even recommended because the application compiled with address sanitizer is really huge. The second one worth to mention is undefined behavior sanitizer. So it's a tool that checks for everything that is in the C programming or C++ programming called as undefined behavior, right? It still can, undefined behavior can work, can make no crashes, but still can generate mistakes that can be found with the undefined behavior sanitizer. The third thing that I found recently is a library called Fuzz. So it's alternative to memory sanitizer. Memory sanitizer is just part of address sanitizer that is used to see if there is uninitialized memories on the stack. So the link for the libdifuzz, you can check it. I haven't, so I don't know how it works, but it seems pretty much. Okay, another step, if you have all the stuff, we need to take our test cases and we need to somehow mutate them. How to do it? Well, AFL has some genetic algorithm implemented, some deterministic, some not deterministic. But what we want to do is to make these mutators improved. How we can do it? Well, first thing is to use dictionaries. So AFL allows to use dictionary, which is a file including the list of the values that we want AFL to include every test. How can we create this kind of dictionaries? Well, by hand. Just type it whatever you want inside the file. You can download it from the internet. There are dictionaries available, for example, for PDF files having all the keywords. You can just parse the source code, whatever you want. You can parse, for example, the applications, looking for strings and then add those strings inside the dictionary. Or you can do it during compilation time. There is a nice plugin called IFL LLVM token cap pass, which is used for generating dictionary. While application is compiling, it takes all the ifs, all the string compares and memory compares, and dump everything to one file. Here is the link for it, and you can test it if you want. The other thing that may help the mutators working much better is not changing the mutators, but changing the application to make it easy for AFL. As you may know, AFL has some problems with some ifs. I think here is the example, right? So on the left, the first if you see something like this. I didn't check this particular value, but I checked different one. If you do this kind of if, AFL won't find it. Doesn't matter how long you will run in it. Pure AFL downloaded from the internet won't find this kind of code. There is no way. Split compare pass as a plugin for a Clang deal with this by changing one if to multiple ifs, which is much better for IFL to find and go through. The second plugin is called compare transform pass, and it does the same, but with the string compares, right? It changes the string compares to multiple ifs, which are very easy to handle by IFL. What else? You can also create your own mutators. This can help you, especially if you have your own application tested or your company testing the application, or you're a developer and you know exactly what kind of application you have, what kind of magic value you are used, so you can do it on your own. For AFL, there is a nice article about how to do it. Here is the link. There is also a libfuzzer module that allows you to add custom mutators to a libfuzzer if you are interested. Okay, so we have all of this, but how about speeding up the application, right? Because even if you make it working faster for 5–10%, if you're fuzzing on a larger scale, it gives you significant difference, right? What you can do? You can do distributed fuzzing, right? I already mentioned about there is this master-slave mode. So how it works? So master mode works in deterministic way. So you say how many masters you want to have it, what master is the number, and it's split up all the search area to those masters. So all the masters need to run. And then you have a slave that works undeterministic, random way, and all this together give very good results. You can see about parallel fuzzing from original IFL, what you can do to make it faster. So this was on one machine, but how you can distribute to different machines? Well, you can do it by simple tricks. So AFLs between every instance is synchronized based on the directory. So one of the tricks that you can use is just use the network share, right? Then you can have access to this one directory from many machines, and then you can build the cluster without adding any other stuff for AFL. Here are tools already designed for that. When they are doing this distributed fuzzing between different computers. What I did in my previous job, we built a fuzzing farm based on the Android devices, and we use AFL, and we synchronize the directory between the devices. So each device had the same directory, and on each device you can run multiple IFL instances. So at the end we end up with 96 instances of IFL, which was divided by 4, like 20-something physical devices. Another technique that you can use is called in-memory fuzzing. One of the most consuming process while you are fuzzing is loading the application. You need to load it. Then the application just runs small test case, and then you need to unload it, right? So better is just to load everything you need, and before the functions that you want to test, you just fork it instead of running the whole application. Make it much faster. So IFL allows that. It's called IFL persistent mode. You just create a loop. Here is the loop. Right? You compile it, and here is the function that you want to test it. What IFL will do will run this while. Here is the fork mechanism, so it forks 1,000 times, and then it will exit the application and run the application again. So we could have much more faster working application. Okay, another thing that is very important is the feedback. Feedback is information going back from the application to AFL, how the application handled the test case. Normally, it's just information, what kind of coverage we have, what basic block were executed, what kind of path we went through. So every new test cases, we can say, okay, this test cases go through the same path that we already seen. It's pointless to test it, right? And we have a few options here. First option is compile time instrumentation. The basic things that was invented by Elkamtov was something called AFL GCC. It was a wrapper for GCC that adds some assembly blocks on every basic block. And based on each time the basic block was executed, this assembly block gets the information what I am. Thanks to this, AFL knows what kind of basic blocks were executed. Right now, AFL have a module to use the LLVM compile time instrumentation. I'm using this module because it's quite easy to add if you're using Clang compilator. Yes. The other thing is hardware tracing. There are two advantages over the compilation time. One is much faster. And the second thing, the application doesn't need to be compiled. This is very important. So we can buy an application, we want to test it. We don't have a source code. We can use under hardware tracing and get very good results. Two most popular hardware tracing technology are Intel PT, Intel Processor Trace, and something called ARM Core Sight. So what is Intel Processor Trace? It's just additional feature inside the processor that gives the information what kind of execution, what kind of addresses were executed. The advantage of this is that there is no overhead how the application is executed. It's done on the hardware. I found two Windows, unfortunately, Windows AFL implementation that can use that. PT Fuzzer, WinAFL, Intel PT Fuzzer that use this, you can test it. Of course, you need to have appropriate processor from Intel. Don't remember what kind of version it starts. So, I have no slide about the ARM core side because I haven't found any implementation for ARM with the hardware tracing. I know that it's still very highly developed, so it's not finished yet. There is only one version of Linux system on ARM that supports this ARM core site. It's much more complicated. It works in a much more complicated way than Intel processor tracing, and you need to decode all the trace, and that's why it's so difficult to implement, or no one needed. The third thing you can do is just use the execution time instrumentation. If you don't have a source code, you cannot recompile the application. You can just use this. There are a few products available, Dynamo Rio, Pin, QEMU, DynEast, and recently very interesting QEMU TCG. They are the tools, frameworks, however you call it, that can inject the code while the application is executed. It's very high overhead, but as I said, you don't need a source code, which makes a very good for a testing. The last thing that I would like to mention is about different branches. So IFL become a very popular tool. And right now, there is a lot of stuff going on around IFL, so it's not just simple IFL. There are different branches available on the market. Whatever you want, you can just look for it. I just mentioned a few. There is one for Android. There is one for JavaScript. There is one for network fuzzing. There is one even for Python modules. So there are many different branches. I didn't mention all of them because there is no space here. The trick is that before you start fuzzing and using the AFL and try to change it, just Google. Maybe someone already wrote an AFL for that. So what next? I have nothing more to say. Just choose the target and fuzz. Yeah. Thank you very much. Any questions? Yes. I cannot provide you a microphone because I don't have it one. Still can hear you.
Huh.
Oh, much better.
So you said that AFL was using genetically determined inputs for fuzzing the data. I was wondering whether it came with a preset of good inputs that fuzzed well, or if I start fuzzing, it will start seeing which ones were successful and start generating new data based on that.
So the original AFL has doesn't have an input. You provide the input, and they have something called mutators. So inside the code, you could see the mutators are, for example, 0, 1, -1, 255, 256, right? These are the mutators that are built in IFL, right? Depends what kind of application you are testing and what kind of set you are providing. It will use those set of mutators and try to fuzz your input. If you don't provide it any, it will try to build from the stuff that they have, right? One of the example is that I show you with this if and the long value, right? There is not such kind of thing inside the IFL. It won't never find this kind of value, right? It needs to go through, iterate all the numbers, right? But there is no such thing. It just sometimes try to random numbers, but yeah, only for that. That's why the trick is to either provide very good inputs, right? You can download all the spectra of how to say, like all the inputs that you're interested, right? For example, if you want to test PNG files, right? So you can create small, big one, color, grayscale, this kind of compression, this kind of compression, this kind of compression, right? This is good input. So IFL know all the stuff, can learn from this, can mutate those files, and do the stuff. If you don't provide this, it still can try to do it, but it may not found it. I had the test when we are testing JPEG files. So I have a whole set of colorful pictures, but none of them were in grayscale, and it never found it any that you can go through the grayscale. So the type of the file inside the bytes that needs to be inside to say, yeah, this is a grayscale was too complicated for AFL, right? He never found it. When I provide just one, then it goes in cascade, right?
And another question, if you had no idea about the inputs you're supposed to provide for your application, where would be a good start?
So, if you have a source code, you have a source code or no? Because this is a crucial question. If you have a source code, you can go what I did in my previous presentation. There is a link you can see. I went with the symbolic execution. So symbolic execution can go through all the path and create you inputs file, right? Even if you don't know what kind of input file, the symbolic execution tool will do that. There are a few problems with those kind of tools. They are very resource and time consuming, but for a beginning is very good. So you can run it for 2-3 hours and get hundreds of new very good test cases, right? The other thing is you can I don't know, for example, reverse it in IDA and dump all the constant that IDA found, right? And add as a dictionary. You can, you can do the same with the source code, right? You can go through all the ifs, all the compares, all the, I don't know, mem copies, whatever, all the constants, and again, add to dictionary and run again, right?
Thank you.
You're welcome.
Hi, Marek. So, if I remember correctly from memory, AFL was originally designed for fuzzing file inputs, right?
Yes.
Is it good now, or is there a good fork for fuzzing network inputs? And does it have to be on the same machine?
So I haven't used it for a fuzzing network input. There is a branch to do that.
Is it a fork or a branch?
Yes. It's a fork of AFL with some add-ons that allows you to fuzz the network protocols, but I haven't seen it.
What about a different tool that will be like at the same level of goodness, like AFL for networking?
I don't know them. It's like the AFL is right now the state of the art, so all of them try to do the fork. The trick is that AFL uses this instrumentation, right? And this is the one of the important thing, crucial things in the fuzzing process right now, right? You get the feedback and you know which input is good, which input is no good. The different approach you can find is a fuzzer called HonkFuzz. I don't know if you heard. So it's also written by one of the guy of the Google. So it uses system perfs. So you can define what kind of perfs you are using from the system, like how many branches you are executing or how many missed branches you are executing. And this kind of stuff is used for a feedback, but I don't know any fuzzer that does the same as AFL, and it's not AFL branch.
Okay, thank you.
Thank you. We have a next question here. Anyone else after? So this will be the last question.
Hello, great presentation. My question is, so if you serve AFL a certain file that has a certain format, can you specify it somehow? Okay, AFL, please mutate this, but ignore this part. For example, ignore the parts that indicate that this is going to be a certain header that needs to be there.
So right now, no, but IFL can learn that. So IFL doing the process of mutating can learn that, for example, this part of the code is not worth to mutate anymore. And this part of the code, it is. So then you can, there is a tool for IFL map or something similar that shows you that, yeah, this piece of the file is something responsible for a length or something, this is for this is for this. So IFL somehow learned that, but I don't know the way that you can say that don't fuzz this piece of the part of the file. No, I don't know that.
Okay, so one other question, if I may.
Sure.
If you had any experience with libfuzzer, can you compare their mutation engines? Which one is better and why? Are they similar?
So they are working in different ways, right? Classic AFL works each time it runs the application, go through everything and exit from the application, right? libfuzzer is just running the same function many times, right? It's very difficult to compare that because sometimes it's happened that, for example, if you fuzz a function that inside use some kind of resources, right? And there is a bug that the resources are not back to the system, and you fuzz it 1,000 times. So at some point it will crash. But you will never get this inside the application because each time the application exits, system automatically release those resources, right? So these are the problems that are not, you cannot compare, right? So everything depends what kind of function. There is no one answer, this is better, this is worse. Everything depends what you want to fuzz, right? The question is also if it's better to fuzz PDFs or images, right? AFL may be not very good with PDFs, it's much better with the image files. The same is here. libfuzzer is for one thing and AFL is for the second thing, right? Or you should use both. The best solution is use both and feed them each other. If it's possible, right? Sometimes it's not, sometimes you just fuzz the part of the file which you feed the function. But if they are the same, use both. Like there is no problem to use 3 or 4 fuzzers. No one said you cannot do it. You can run different fuzzer and feed IFL with the inputs. There is no problem with that. Just whatever you have, you can run it, right?
So this was Marek Smizwowski from Sysura. Thank you very much.
Thank you very much.